Hello, Tiara. Okay, we got Deborah, we got Tiara. How you guys doing? Now I can't talk.
I'm pretty good. How are you?
I'm good. Deborah, did you send me your homework?
My quiz, you mean?
Yeah, the quiz. Yeah.
I think I did this morning, yeah.
Okay, that's fine. I looked early this morning, so I probably got it. Yeah, that's
Okay.
fine. Okay. Tiara, I know you sent me yours because I saw it last night, I think. And whatever. I'm trying. We're gonna start. I'm gonna wait for Dion and Alexis, but we're gonna sort of. I got sort of stuck in the middle of what I was doing yesterday, so we're gonna do a quick review and then we'll start into what we were doing. So so guys, we are almost finished with this series business, but we got one more big kind of section to do before we finish it. And I'm going to take some time. I may finish that section today, but I'm going to take some time tomorrow to just throw out some problems and see what we can do with them. Okay, so we need practice at these things. Okay, it's sort of like we did with the integrals. I said, okay, here's 100 of them. What are you going to do? Okay, now I'll just throw out one and say, what are you going to do? So what's going to help you with that, if you want to start looking over it, is that guide I showed you yesterday and said, well, if it's a positive term series, do this, this, or this. But tomorrow, what's due tomorrow? Let's see. Is there anything due tomorrow? I'm trying to think.
Yes.
Yes. Which one is it? Is it
comparison thingy?
Say it again.
Comparison.
So the limit. Oh yeah, the comparison test. Okay.
Mm-hmm.
So if
you want to
today, let me let Alexis in. We'll start today looking at some of the comparison tests if you want to. If you want some homework, we'll look at those and then we'll pick up where we left off yesterday. Okay, Alexis is on her way. Dion, I hope, is on her way. Let me go ahead and try to share the screen while I'm waiting for Dion to get here. I've been having bad luck with my internet this morning, guys. So if I go away, I'll try to come back like I did yesterday. I don't know what's going on all of a sudden. All right, let's see. There's that. Okay, who have I got? I got Tiara, okay, now I got Alexis. You're here, Alexis. Okay, so guys, while we're sort of waiting, you've got, and there's Dion. Okay, so hang on. Get her in. Okay, she's coming. The quiz that's due tomorrow, and I'll just say tomorrow by the end of the day, okay, by 5. I really want to get these things graded before the weekend, because we're coming up on our last series test. So I want to make sure where you stand on that. And as I said, tomorrow we may take some time to do some just random practice on these things and say, what would you, and sort of line up things and figure out what it is we know and what we don't know. So anybody have any questions on those, either the basic comparison test or the other ones, the limit comparison test? Did anybody, all that stuff was on in section 11 point, blah, 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 11.3. Okay, and let me point out something because it makes a difference as to what we're doing now. All that stuff in 11.3 was positive term series. Those are the ones you want to apply these basic comparison tests to. Yesterday, we started talking about alternating series, okay? Alternating series are not positive term series because they can alternate. There are series that have negative terms in them that don't necessarily alternate. I might have 2 positive, then 2 negative, or 2 positive, then 2 negative. But all of this limit comparison and basic comparison is are positive term series, all of those. We will not use the comparison test necessarily on any of these other things, except in one specific case I can think of. Okay, so so anybody have any questions on the homework? Just looking at limit comparison, basic comparison. Anybody have any problems? Now's your chance. Now's your chance, or I'm gonna give you one. I'm gonna give you one whether you ask me one or not, but I might give you some even ones. I still want you to look at the odd ones.
You might as well give us one.
All right, okay. Does that mean you hadn't gotten around to the homework yet? That's not good. You need to catch up with this stuff.
The show was real.
Yeah. Suppose I said this one, guys, and I want to say I've got a series, and it's n to the 5th plus 4n cubed plus 1. And we're over 2n to the 8th plus n to the 4th plus 2. Now, let's chat about this one first. That's an 8 power there, okay? Number 1 is positive term series. Your series starts from 1 to infinity. It doesn't have any of that alternating stuff on it, so it's just this series. You want to know if it converges or diverges, and that's the only possibilities when you have positive term series. I will start out by saying this one looks a little too complicated for a basic comparison test, okay? It's hard. You got so many different things here. So what I'm thinking is that it might be limit comparison test. And what we said we were going to do in a limit comparison test was sort of compare the highest powers in the numerator and the denominator. And I don't even really care what the, I don't even really care what the coefficients on those things are. So somebody give me an idea about, if I want to use limit comparison test on this one, what series would I want to compare it to? Somebody started to say something.
Would it be n to the 8th?
Well, the n to the 8th makes a difference, but let me say this. Again, I said, let's try to compare the highest in each the numerator and the denominator. Because remember, the limit comparison test takes the series you're comparing and the series you had and putting one over the other and then trying to find a limit. So if I compared n to the 5th and n to the 8th, what would n to the 5th over n to the 8th be?
1 over n to the 3rd.
1 over n cubed. All right, here, that's kind of the way this thing works. If I looked at that, 1 over n cubed, and I said, you know, I think I'm going to try the limit comparison test on this. And what the limit comparison test does is it takes a limit of the following. It takes a limit as n goes to infinity of the nth term of the one you're interested in. Oops, n to the 5th. Oops, not that. N to the 5th plus 4n cubed plus 1 over 2n to the 8th plus n to the 4th plus 2, and puts it over the one that you picked to compare it with. So 1 over n cubed. So that's the limit comparison test. That an is the one you want. I mean, when you're looking at, bn is the one you're comparing it to. Here's what the limit comparison test says. They either both converge or they both diverge. So you have picked one you know something about. And you've picked one that you think's probably going to make you be able to take the limit here. We'll talk about that in a second. What do you know about 1 over n cubed?
It's the P series.
The P series with P bigger than 1. What do you know about it then?
It converges.
It converges. Okay, so now here's what the limit comparison test says. Let's look at the limit of this one over that one and see what happens. If you note here, the limit as n goes to infinity, if I invert and multiply this thing, in the top, I'll end up with n to the 8th plus 4n to the 6th plus n cubed. Okay, I just inverted and multiplied. And then I'm left in the bottom with 2n to the 8th plus 4n to the 6th. Well, sorry, plus n to the 4th. Sorry, I messed that up. I was looking at something else. The one up here, n plus n to the 4th plus 2. Now, you see what I did? I picked something that made the powers in the numerator and the denominator, when I put one over the other and I inverted, I made it so the powers came out the same. And I know that this one converges. That's easy to take the limit of. What's the limit of that one, guys?
A half.
It's a half, isn't it? What the limit comparison test says is this, and if you want to look at exactly where it is, it's where is it? It's on page 549, and it says if that limit is some constant bigger than 0, then these either both converge or they both diverge. Because we picked one to compare with the limit comparison test, we know that it converges. We'll say, therefore, according to the limit comparison test, we'll call it LCT, by LCT, the original converges. This thing right here, the sum from n equal 1 to infinity, whatever we started with, n to the 5th plus 4n cubed plus 1 over 2n to the 8th plus n to the 4th plus 2 also converges. If we had picked one that diverged, then they both would have diverged. Okay. I'm gonna give you let me give you guys one and let you work on it and let me see what happens here. Let's try this one. All right. So did somebody, everybody's here. Okay. So what I'm gonna do is give you this one. What about the sum from n equal 4 to infinity, and by the way, it doesn't matter where the series starts, guys. This one just happens to start at 4, of 3n over 2n squared minus 7. Now, let me tell you why it does, well, they've got it starting at 4. It really doesn't matter where it starts. You just plug in 4 first. All right, I want you to run a limit comparison test on that and see what you get. Now, I want you to figure out what series you know and what you want to do with what I did a minute ago and tell me whether this thing converges or diverges. So guys, based on what I said about figuring out a way to choose things, tell me what series you chose to limit compare this with.
1 over n.
Yeah, 1 over n. And what do you know about 1 over n?
It diverges.
It diverges. Okay, so what we're going to do is we're going to look at the limit of this one, this nth term over this one. When I invert and multiply, when I invert and multiply, I get the limit as n goes to infinity of 3n squared over 2n squared minus 7. That's 3/2. It's certainly a constant greater than 0. The limit comparison test says if the one you're comparing it with diverges, then so does this. So therefore, by the limit comparison test, and you're going to need to tell me what test you're using anytime we use these things. This one we started with n equal 4 to infinity of 3n over 2n squared minus 7 diverges as well. They either both diverge or they both converge. I didn't prove that, guys. The proof was a little bit long for me to do this time when we're sort of short on time, but that's what it says. Let's say, is everybody okay with using the limit comparison test on that one? Let me say a word about the other test, that basic comparison test, since we're talking about it. I'm going to look at this one again from a different point of view, and I think you'll agree that the limit comparison test is an easier test to use. So 3n over 2n squared minus 7. 3n over 2n squared minus 7. So if I wanted to use a basic comparison test, I'd want to see how this compared just the whole thing compared to another series and see if what dominated what. So maybe I can do this both ways, or maybe I have to use limit comparison test. Now, I'm going to compare it to, let's say, or I'm going to start by saying, well, why don't we do 3n and we'll drop that minus 7. This is where I most often use the basic comparison test, where I can just drop off a constant and I can tell something about the fractions. So if I were just to drop off a constant right there, which of these which of the denominators is a bigger number? Which is bigger, 2n squared minus 7 or 2n squared?
2n squared.
2n squared is bigger, right? So this, if I were just looking at the denominators, 2n squared would be bigger than 2n squared minus 7 because I took away 7. But remember when I flipped the fractions, it looks like that. Okay? So does everybody understand what I'm saying? I flipped the fractions. I mean, 3 is less than 4, but 1/3 is greater than 1/4. So I flip it.
I understand it, but you know, it takes a while to.
It does. It takes a
Yeah,
while to process it. That's why I kind of like to look at just the denominator and say, okay, that's the, and sometimes I'll even write it. That's the bigger denominator. That's the bigger denominator. So that one's going to be the smaller fraction. Okay. So that's or the, yeah. You have to kind of think through it. That's bigger than this. So I might, if I would just look at the denominators, I'd say bigger than, but when I flip them, or when I put it in the denominator, it's going to be, it's going to flip this sign right here. You really do have to think about it. That's why this is a little harder to use the basic comparison test. But let's see what it says. Let's finish up and see what the basic comparison test says. This thing right here is just 3/2 1 over n. Now, if we looked at both of these things as series, what would happen in this series right here, the 3/2 1 over n? What would it do? It would diverge because it's just a constant times the harmonic series, right? And then that series would be divergent, and it's less than this one. So something that's bigger than a divergent is also going to be divergent, so we would arrive at the same conclusion using the basic comparison test. So you have to, if you've got a smaller one diverging, then anything bigger than that's also going to diverge. That to me, but to me, it's much easier to use the limit comparison test in this. But you could do it either way. You could do it either way. Okay. Oh, let's see if I got another one here. Let's see. what if I had 1 over, let's go back this way here. What if I have 1 over, and the series is going to go from 1 to infinity of n times n plus 1 times n plus 2. It's in a little sneakier form, but you should be able to do it. Decide, and I'm going to say that that's too messy to use the basic comparison test on. So I'm going to say try to use a limit comparison test on. So guys, what are you trying to use? Anybody?
I use 1 over n cubed.
All right. Actually, that's a good choice. Alexis, tell me what you saw that made you think you wanted to use 1 over n cubed.
3 n's in the denominator.
Good. Exactly. 3 n's in the denominator. You know what? I'm not even going to waste my time multiplying that stuff out. If I look at just the first 3 terms, n times n times n is going to be 1 n cubed. So I'm going to look at the limit. Oh, and by the way, what does this one do right here that you picked?
Converge.
Because it's what?
Positive. I mean, because it's more than 1.
If p is more than 1, it's a p series where p is bigger than 1. Okay, so we know this thing converges. So when we use the limit comparison test, will be the limit as n goes to infinity of 1 over this n times n plus 1 times n plus 2 over 1 over n cubed. And when I flip it there, it's the limit as n goes to infinity of n cubed over n times n plus 1. And again, I don't need to multiply it out. I know that there's going to be an n cubed in this, so what's the limit actually going to be, guys? It's just going to be a 1, isn't it? Because I got n cubed down here, and that's 1 over 1. That says, because it's a constant, it's greater than 0, by the limit comparison test, both converge or diverge. We already said that one converged, so by the limit comparison test, the one we started with converges.
I use the basic test.
Say it again. Say it again.
I use the basic test. What is it called? The basic?
Basic comparison test. On which one?
This one.
Okay, tell me, so did you not use the limit comparison test?
No, I guess
Okay. Actually, let's see.
Supposed to.
Well, let's see. Well, I mean, it doesn't matter. I mean, if both of them work, that's great. So you were taking this one, 1 n times n plus 1 times n plus 2. Okay, tell me what you compared it with. So Alexis is trying to use a basic comparison test here. What'd you compare it to?
The same thing.
1 over n? Okay. Now, let's decide, let's just look at the denominators for a minute. The denominators, which is this? What?
It was 1 over n cubed.
Huh? 1 over n cubed? Okay, fine. That's fine. So, okay. Now you might really need to multiply it out to see something, but tell me which one you thought was the bigger one.
The 1 times n plus 1.
Okay. If I multiply this out, let me say a couple things here. If I multiply that out, that'd be n squared plus n times n plus 2. If I kept going, it would be n cubed That's 2n squared plus another n squared, which would make it 3n squared plus 2n. Okay, now let's look at it in its multiplied out form. Which is the bigger denominator?
I really don't know.
Well, look at it. This one's got an n cubed and that's got an n cubed and this got stuff added onto it.
Oh, then the other stuff.
All this up, this is bigger. This is a bigger denominator, right? So in other words, this denominator right here is bigger than that denominator, which means what about the fraction?
Switching the sign.
Fraction will be less, won't it? Okay, so actually this is not a bad idea because we know that that's a convergent series right there. And it dominates this one. So anything that's smaller than a convergent series, so if we look at the whole thing as a series, anything that's smaller than that will also converge. So either way we get it. Either way we get it. That's a good example. Okay, so basic comparison test works, limit comparison test works. Does everybody see why you can use both of them? Compare the denominators on these things. This is clearly the bigger denominator, which means the fraction is going to be less. If you got a convergent series dominating something, it will also converge. Okay, great example actually. I would not have thought to use the basic comparison test on that, but it will work. All right, let's try another one. One more, and then we'll go on to what we were talking about on Wednesday. What if I had ln, the sum from n equal 1 to infinity of ln over n cubed. Natural log of n. Is that it? Yeah, natural log of n over n cubed. Guys, if I said to you, well, do you think you could use limit comparison test on this? What would you try? Tell me what you would try. LN's kind of a thing all on its own. So I might say, well, why don't we try 1 over n cubed? I don't know this is going to work, but we're going to try it. So suppose I did want to compare it with 1 over n cubed. 1 over n cubed does converge because it's a p series. But if I tried to take the limit as n goes to infinity of ln of n over n cubed over 1 over n cubed, I would get the limit as n goes to infinity of natural log of n. The n cubes would cancel, wouldn't they?
Mm-hmm.
What's happening to the limit of log n as n goes to infinity? What's log n doing?
To infinity.
It's going to infinity. Remember, it's that curve that goes up like that? It goes to infinity. The limit comparison test will not work here because you need to get a constant there. So if the limit comparison test won't work, then maybe I need to use a basic comparison test here. So let's finish it off. All right, let's try again. Let's look at ln over n cubed. Now, I actually sort of talked about this the other day. I think I may have said something, so you may recognize what I'm getting ready to say. If I looked at the function y equal x and the function y equal the log of x, then y equal x is bigger than log x. So I could actually compare this to the following. That's the log of n is less than n. So if I replace it with a lesser numerator, I'm going to get log n over n cubed is less than n over n cubed because n is bigger. The numerator is bigger. If I simplify this, it would be 1 over n squared. Now, what do you know about 1 over n squared?
It converges.
It converges, and it's a p series with p greater than 1. So it's a convergent series that dominates that. In other words, it's bigger than or equal to that. Therefore, this one converges. So there's one where limit comparison test doesn't work at all, but you can do it with a basic comparison test. All right, do some of that homework. The more you think about this, the easier it gets, okay, after you have the initial headache, okay? All right, let's go back. Let's see where I am here. Let's go back to what we were doing yesterday and talk about how this is different from all the limit comparison and basic comparison tests. Sections 11.3 and 11.4, that was basic comparison test, and actually we didn't even do 11.4, guys. I don't even know why I've been writing that. It's on something called the ratio test, and we haven't done that yet. But it's, so I'm just gonna mark that out there. In 11.3, those tests were basic comparison tests, limit comparison tests. They work for positive term series. Yesterday we said, what if our series does not have all positive terms in it? In other words, we looked at a special case where the terms in the series were alternating. So remember, this -1 to a power makes it alternate because it goes back and forth between even and odd powers of -1. And we said that here's an example of one of those. If I put in 1, I'll get 1 to the 0 times 1 over 1, which is 1. If I put in 2, I'll have an odd number, so that's -1/2. I put in 3, I'll have an odd number, so that's 1/3. That is an alternating series, okay? You cannot use the basic comparison test on this. There's something that might happen with it that's gonna help us in the end to know that, but you can't use it on there, okay? It is an alternating series. So we've got this test called the alternating series test. And the alternating series test has 2 things. You have to check both of them. You're gonna get a convergent alternating series if these 2 conditions hold. This one and this one. Now, AK bigger than or equal to AK plus 1. Now, AK plus 1 is the term right after AK. It's the one next after AK. And that means it's less than that. So what this says is that your series has to be, the ANs in your series have to be decreasing. So let's go back for a second. If you look at these without their signs, just the AN part of it, guys, this thing right here, this 1 over n is the AN part of it. 1, 1/2, 1/3, 1/4, 1/5, they're definitely decreasing, okay? Also, if you look at these things, if you just look at the AN, the limit as n goes to infinity of that is 0. If you have both of those conditions met, you can say that the alternating series converges. It's an easy test to use. But the harder thing about it is it's easy to see that was decreasing. It's not always easy to see that some of them are decreasing. But those are the 2 conditions for alternating series. Okay, so if we look at this in the context of what we did there, is 1 over k bigger than or equal to 1 over k plus 1? Yeah, because that's a bigger denominator. A bigger denominator means a smaller fraction. So that thing is decreasing and the limit goes to 0. Therefore, that thing we just looked at converged. Now, let's look at the examples we did yesterday, sort of run back over them. The hardest thing in this test to do is to find the decreasing, not necessarily to find out whether the limit goes to 0 or not. Because if you look at this thing, the limit clearly goes to 0 of this thing because the power in the numerator is lower than the power in the denominator. The denominator's growing faster. It's getting bigger faster. So that's going to 0. So the second thing is condition is met. Decreasing. There are actually 3 ways to show decreasing if it's not obvious that it's decreasing. The one that we did yesterday was say, think about it as a function and take its derivative. If its derivative is negative for 1 or above, because we're only interested in 1 or above, guys, because we're only interested in this thing for values of n equal 1 and over. If the derivative is negative, you have shown it is decreasing. So what I did yesterday was I took the derivative of this thing using the quotient rule. The bottom times the top, my top times the bottom. I played it out. It was 8x squared minus 16x squared was minus 8x squared minus 6. I pulled the minus out of that. The bottom's always positive because it's squared. This is always positive because you're squaring something, multiplying by positive and adding something positive. That negative makes this whole thing less than 0. I can say it is now decreasing. So I proved decreasing, and I showed the limit as n went to infinity of this part of it up here. This is the an part again. Went to 0. Therefore, by the alternating series test, and that's how I'm going to want you to write things, guys. Tell me what you're using. By, and we can talk about that as AST. By the alternating series test, that series I had up there converges. Okay. Now,
So we have to do like both of these things?
yes, you need to do both of them. You need to do both of them. Technically, actually, I'll say this. If it's an alternating series and that one doesn't go to 0, then since both of them have to hold, you really could stop right there. I mean, because I'm gonna make sure that doesn't happen. I want you to see that, I want to make sure that you know how to show something's decreasing too. Okay, so try both of them. Okay. Now, there are two other ways to show something's decreasing. You could show that the difference between those last two terms you were looking at, remember a minute ago we were looking at something like a 1/3, a 1/4, a 1/5. Those were my AN terms. This might be A3, A4, and so on. If A4, if AK, sorry, this one right here, this one, AK minus AK plus 1, the next one in line, is positive, then you know it's decreasing because you're subtracting something smaller that came after it from something bigger. So you can remember that. If you can show that AK minus AK plus 1 is bigger than or equal to 0, you also have decreasing. Because you're subtracting one later, the AK plus 1 from the one before. If it's greater than or equal to 0, then that second one has to be positive. So here's what I do to do that. And I'll run through the algebra pretty quickly, but it's not hard. I put in the AK, I put in the K to the series. Then I put in the K plus 1. I would like to show this is greater than or equal to 0. So if I multiply this out and find a common denominator, blah, 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 make it as simple as I can, it looks like that. Okay, it looks like that. Now, because K's are always bigger than or equal to 1, this is positive, that's always positive. So that says that the term, if you subtract the later term from the one right before it, you're gonna get a positive number. That's a generic way to show that. So that's another way to show decreasing. And along with the fact that the limit goes to 0 as n goes to infinity, we have it. There's one other way to show this. It looks like this. If you got a lesser number, that's the last one you looked at, and this is the one right before it. If it's decreasing, then the lesser number over a bigger number is going to be less than or equal to 1. So, for instance, if we had the way we had the 1/4, we had the 1/3 and the 1/4 here. This is my AK plus 1. This is my AK. If you put 1/4 over 1/3, you're going to get 3/4, and that fraction will be less than or equal to 1. Okay, so if that's true, it's also decreasing. Take your pick. Pick whatever you want to do. But let's do that. My AK plus 1 would look like this. I took that series I had up there and I plugged in just the K plus 1 to it. And then I took AK. So that's a K plus 1 on top. That's a K on the bottom. I inverted and multiplied. I canceled the 2's. I have then K plus 1 times 4K cubed minus 3, and I didn't even, there's a K down there and that. When I crank that out, and this might be the harder one to see, but when I crank all that out, here's what I get. Now the question is the denominator bigger than the numerator? Because if the denominator is bigger than the numerator, this is less than 1. It's 3, you get 3 over 4, you got something less than 1. Let's sort of match the terms up and see about that. These would be the same. Which would be bigger or smaller, 4K squared or 8k squared?
8K.
Smaller. Now I'm talking about just comparing these two terms right here. Which one would be smaller? 4k squared. If k's, remember k is greater than 1 because we're looking at a series. Okay. So which will be bigger, 8k squared or 4k squared?
8.
8k squared would be bigger. So you got something bigger in that denominator. Same here. Which would be bigger, k or minus 3k?
I mean, K.
The k, yeah, because I mean, remember k is bigger than 1. So all along down the line, and then I subtract 3, that makes it even less. This is less than that. And if this is less than that, it's less than or equal to 1, and so you've got decreasing, okay? Those last two are a little messy. I mean, you're a little more familiar with taking the derivative, but to find increasing or decreasing, but those two work sometimes when that doesn't. Okay, let's take a look at that. Keep that in mind as an alternate way to show things are increasing or decreasing. Okay, this is where we were having our discussion yesterday about that telescoping series that Tara got right. And I didn't even think about what was going to happen. It did come out to be negative. Everybody else didn't know the problem, which I'll look at when I look at the homework. Okay. So let's look at something else. I have a few more things I want to add in the last 10 minutes, and then we'll pick it up again tomorrow. There are my examples right there. All of those things. So I'm going to go, let me go back here, guys. I've got a new part of this lecture. I'm in the same section. It's 11.5. If I can find it. I've got so many lectures in right now. Let's see, let's go down this way. Alternating series. Here we go. Alternating series continue. And again, this is 11.5, not 11.4. Okay. So let's talk about something else that could happen. What if a series contains both positive and negative terms, but it's not alternating? There is a way we can look at this, and it's something called absolutely convergent. And actually this works with alternating series too, because anytime you've got positives and negatives, the definition will work. The definition says a series AN is what we call absolutely convergence. And that's absolute because of the absolute value, not absolutely right, not the word absolutely. Never mind, I don't even know what I'm trying to say, but it's because of the absolute value. If the series AN with absolute values around everything converges. So in other words, if it had positive and negative terms in it, it's all now going to have positive terms. So the series AN is called absolutely convergent if, when you take the absolute value of it, it converges. That's just a definition. So take it for what it is. Let me give you an example. Suppose I looked at this series right here. It's alternating. Let's see. I think we can look at this one pretty easily to see whether it converges or not. If you look at 1 over n squared, that goes to 0 as n goes to infinity. And if you differentiate it, if you looked at x to the 1 over x squared, we looked at 1 over x squared and wrote that as x to the minus 2 and took the derivative, it would be minus 2 over x cubed. And since all my x's are bigger than 1 in a series, that's negative. This thing is decreasing. We know it converges by the alternating series test. It converges by the alternating series test because this thing goes off to 0 and you can show it's decreasing. Okay, so the next question is it absolutely convergent? Well, absolutely convergent means to take the absolute value of every term you see here and see if it's convergent. Well, if we take the absolute value of every one of those things right there, it's going to change all these negative signs to positive signs. How about that one? When I do that, when I take those absolute values, does that thing converge? Well, it's 1 over 2 squared, 3 squared, 4 squared. It's 1 over n squared, isn't it? In other words, if you looked at this right here, and you took the absolute value of something times something else, the absolute value of any of these negative ones is going to be 1. You're going to be left with a p-series. When does a p-series converge? When p is bigger than 1. So the answer is this thing converges. So we say that that original thing is absolutely convergent. So not only did it converge, which we showed by the alternating series test, but it converged absolutely because of its absolute value terms converged.
So like this stuff is when it is still alternating?
Yeah, you're still looking at, yes, you're still looking at this series, the original series right here, okay? So
I just wrote it down wrong.
yeah, it's this one with the alternating series, okay? So we showed it converged by the alternating series test, and then the question is it absolutely convergent? The answer is yes, because if I take all the absolute values, I also get a convergent series, okay? That's all it means. So we call it absolutely convergent. When we have mixed things, positives and negatives in a series, we're gonna want to know whether it's absolutely convergent or not. Because absolute convergence actually turns out to be important. All right, let's look at another one. Let's look at this one. Let's look at the alternating series test. If you look at this right here, and this one, this is this series right here looks like this. If we write what it looks like, guys, if we let n be 0, it'll be minus 1. If I put in n equals 0, it'll be minus 1 plus 1 over 2 minus 1 over 3 plus 1 over 4, and so on. Minus 1 over 5. I think I started at the right, at a negative there. I want to know if that thing converges. Well, 1 over n, or 1 over x, the function 1 over x, for x is bigger than 1, does decrease. The derivative's negative, and this certainly goes to 0 as n goes to infinity. So by the alternating series test, this thing converges. By the alternating series test, that thing converges. Now, the next question is it absolutely convergent? What does it mean to talk about absolute convergence? What it means to talk about absolute convergence is if I took the absolute values of all of those, would I get a convergent series then? What if I took the absolute values of all of those? What series would I get?
1.
Harmonic.
1 plus a half plus a third plus a fourth plus fifth, which is harmonic, which we know does not converge. So we say, if I ask, is it absolutely convergent? You will say no. Because even though the original alternating series converged, the absolute values of all its terms gave me something that was not convergent. Okay? Now, there is a name for this when this happens. When your series converged, but its absolute value pieces in a series did not converge. So one more definition. A series is called conditionally convergent if AN converges, but the absolute value of AN diverges. Guys, the thing you want to keep in your head about this is that example that I just used. Okay? So an example of a conditionally convergent series is this one right here. It's not absolutely convergent because when you take absolute values, you get a divergent series. So basically, if you get one that converges, but it doesn't absolutely converge, it's called conditionally convergent. You got to sit down and think about that for a little while. Keep some examples in your mind. Okay? So this one's convergent, but it's not absolutely convergent, it's conditionally convergent. Okay? All right, because the next one I've got a lot to say about things from now on, I'm going to call it quits today, right here. I'm going to tell you that in 11.5, in 11.5, up to this point, on page 565. Determine whether the series satisfies the conditions. Basically, guys, all you can do right now is 1 through 4. That's it. That's all you can do tonight. So what you're going to do tonight, you're going to go back and look at your limit comparison and your basic comparison, and you're going to do that quiz for me. Okay? And hopefully that'll come out well, now that we've sort of reviewed it. Okay, so everybody more or less happy? More or less? I keep checking out movies to watch at night, and as soon as I finish my work, it's like midnight, and I'm like, am I really going to watch a movie till 2 a.m.? And the answer is no. So I'm assuming that y'all aren't watching a lot of movies either because you got so much work to do, you don't have time to watch movies or binge on Netflix, right?
You know, some days you just have to say yes.
Well, you know what? Here's what I'm going to do. I got a lot to do today. I got papers to grade and everything, but right now I got that movie, and if I don't get it back to Redbox by like 5 o'clock, they're going to charge me for it again. So I'm shutting you guys out, and I'm going to go watch the movie. Okay? All right. I'll see you tomorrow.
I want to.
Bye.